So this talk is about graph theory, basically how we can extend a classical convolution, linear convolution to max plus algebra. So it's the main plan of this talk is first of all I would like to motivate you to work in this topic. It's really nice. So the second one is to explain what we did in our paper, the main contribution, and some simple examples about it. So basically what is what we call a graph signal processing is so we have a graph, so we have some edges or nodes, we have vertices. So that is the classical graph theory. In signal graph theory, we have a signal associated with each edge with which node in the graph. So basically, from image processing point of view, we can say that we have an image where we don't have a uniform sampling. So we have here we can see some image, and the node, the pixels of the image are not well placed as we usually have in a digital picture, for example. So basically, the notation, I'm gonna use G as the graph, V the vertex, and E the edge. So the main idea is the main idea is why we want to formulate convolution and change the algebra on graph. This is because many of the discrete versions of problematics that we are interested in can be formulated as graph problem. For example, but that is the classical image processing is a particular case of graph signal processing, as well as non-uniform sampling, as I said before, and more complicated cases. For example, we can see in this that we call texture mesh. We have 3D structures. We have a node. In each node of the image, we have a color information. So in somehow, we want to define a theory to analyze this, all of that example the same way. So now also especially in machine learning and pattern recognition, we are working on graph of image. This is mainly meaning that each node is an image and the connection is a similarity between them. Or some classical example of graph is a social network Facebook, where we are the node, and the way that, I mean, there are many variables that people can measure on us. And maybe the reason that's why I'm in this session is because some graph can be used to discretize some manifolds. So to illustrate the result of this paper, I'm going to show the example B and C most of the time. So what I want to explain here, the first thing is how we can do diffusion on graph. That is very well known from many years, and a motivation that why we want to extend this idea of blurring convolution to max plus algebra. We have two ways to do it. We want to show you. I want to show you some advantage of one against the other, and one unexpected link that we can see is we want to see that one particular case of the transformation operator that we define solves a well-known problem, the mean curvature on graph, motion by mean curvature on graph. So what we need to know is we have a function between vertices and a real line, and we want to define a transformation between these spaces, meaning that we want to modify the function that we are defining on the graph, and we only gonna use the adjacent matrix as information from the graph. So we have the data is a graph. That is, the graph is the adjacent matrix, and on the other side we have in each node we have a signal. So that is what we need to define the convolution, the blurring, and some operators. So in this case, is basically we have the graph that is in red lines. We have nodes. That is information that we keep in the adjacent matrix. And on the other side, we have for each node a color information. In this case, black or white information. That is the signal. I have two structures, the graph and the signal. So I'm going to start with some basic definition that we need to extend this idea of max plus convolution to graph. The first is a classical definition of upper level sets. So we have a signal on the graph. We can define upper level sets as usual. That's really easy. We have different values of lambda. We can define like this is binary upper set on the graph according with the value of the function, because we have a function on each node of the. That is simple. One important. The same example in the mesh. The same result in the same mesh example. So one important thing is we can have, that is classical as well, we have a threshold linear superposition. We can recover the original signal on the graph by integrating the upper level set. That is simple. So well, the first proposition on the paper is we can show that the operator that commute with the thresholding follow these properties. The first one, that is this class operator is closed under minimum, maximum, and composition. It forms a vector space. So that is only a theoretical point property. So I'm going the wrong way. So the second component that we need is the diffusion on graph. That is basically a discrete version of the classical head diffusion. So we can see that from this linear differential equation that we can solve it. That is the classical head differential equation on graph with L. In this case, is the Laplacian of the graph. It's not the adjancent matrix, but the Laplacian is basically the identity minus the adjancent. So in graph, in this discrete version, we can solve directly by substitution. That we can see that this expression, that is basically the exponential in a matrix version of the Laplacian, solve these equations. If we want to see in detail what this equation is doing, we can see only the first degree of the Taylor decomposition, Taylor expansion of exponential mapping. We can arrive to this equation. This equation is basically meaning is giving us the information that what we have to do in each iteration of this equation is, that is an approximation, but we can see that we have W is the same adjacent information that we defined before. So we have edges. We have this adjacent information in W. So meaning we have a value between edges. They are not necessarily symmetric. You have a function in each node. So what we are doing here is basically a convolution for each node of the image. We are doing a convolution by taking in consideration the information of the neighborhood for a node n, only the neighborhood. And the head flow on the graph grows proportionally with both the temperature difference, that is basically this expression, and the weight. So we have two components. So that is simple. It's an approximation of 1 degree, but it's only to say that on graph we can apply this idea of diffusion. No? That's well known. We can see. So we have a sigma here is one parameter to control the degree of blurring or diffusion. So we can see some results. Okay, we can go further. So that is classical and well known. We can prove that we can apply basically. We have a function on the graph. We compute the upper level sets. We do the diffusion in each upper level set. We can and we do the integration. If we want to have the same original diffusion, that we take the whole function. That is important because for the next proposition we want to use this idea. So So what is the contribution of this talk? Is basically we know how to do convolution or blurring in what we call max times or the classical algebra. So we want to extend this idea of convolution to max plus algebra. So I know that we are not really familiar with this idea of max plus algebra, so that's why I put this diagram. So we have, in linear case, most of the research is basically trying to find a good weight between edges to do the diffusion. We have the bilateral diffusion, etc. And we have yesterday I realized that people working in consensus analysis insist this same idea and try to define the good W or properties for W to have a convergence or idempotence by iteration this expression. So in the world of max plus algebra, we don't have only one convolution. We have two. One taking the max plus the neighborhood is the same, changing the addition for the max and the times for the addition. We have two operators, one for associated with the max and second with the mean. But at the same time, what we gain is if we have something that in theory we call a Galois connection, we don't have to care about the idempotence, because we know that by convolution of these two operators, we want to have idempotent operators. We want to have two idempotent operators. And at the same time, we have this operator. We can have as well an order relation between these two operators. So we can take by difference the objects for different sizes, and we can have also an scale space decomposition. That is well known. So this paper, the theorem of this paper, it shows that how we can, what we have to have in W to have a Galois connection on graph. That is basically why we do that, because we have many other results about that. So it's too slow. So what we did is we find a simple characterization for W. So basically, you want to have this ideal Galois connection that I'm going to show you later the definition. We only have to know, well, we only have to have W between minus infinite and 0, and that's all. So that is simple. We only have to consider weights, negative weights. That is important because we don't have a symmetry. That is in most of the cases in linear. Well, in linear case, mainly you have to have a double stochastic matrix to have this idempotence. Here we only have this simple characterization, and we have to define this. That is max plus operator. That is classical one. The second one, if we have this relationship, we have a Galois connection. So that is meaning in the left side we have the dilation. So G is greater than the dilation, and the right side we have F, or the erosion is greater than the F. So that is a simple characterization to have everything in max plus convolution. So I don't want to show you the proof. So that basically this thing. We have this Galois connection. We have everything idempotent operator, and we have many of the properties on nonlinear filtering. So one example of the result is we have this. That is the original signal on the graph. This is erosion. This is dilation. So basically, max plus mean plus with the conjugate. So what we can see that we call this operator dilation, because basically objects are dilated. So we see, okay, it's dilated according with the order that we have in the signal. Here I apply in each. We have 3 channels in each node. So we have a light object, larger light object in the dilation. We have a darkest object are larger in the erosion. That is classical. That is a classical result in image processing, but we now apply in graph theory in a proper way. So we have this max plus algebra approach. So the second part is about how we can use, take advantage of diffusion to define a family of operators. So basically what we already see, we have an upper level set, we already see diffusion. So we define a new operator that is basically, we have the signal, we do the upper level set. In each level set, we apply a diffusion. So that is basically, this one is a binary function because it's upper level set. We take the diffusion and we integrate after that. So we have two parameters. L is because we do the diffusion on the graph. We need this idea of Laplacian, and theta is the value we do thresholding. So that's important because lambda here is the value of the upper level set, and tau is the value we do thresholding on each one of the level sets after diffusion. So we have some properties. Okay, it's easy to show that we can apply the same. By definition, the operator is thresholding linear, but we can decompose by level set because the definition that is simple to show. We have these order properties in tau. That's interesting. If we increase the value of tau, we keep the order between the result of the operators. So that is basically we threshold. We have a larger value of tau. The output of the operator is going to be higher as well. And we keep this idea of increasing in between signal on the graph. You have one function larger than other. After the operator, for every tau, we keep the order. And one important thing for a practical point of view is if we have, instead of the Laplacian, we have a ball. I mean, this is a completely isotropic Laplacian. We have that with tau is close to 0, we basically want to have the same operator dilation that we defined previously. And in the case with tau is close to 1, we want to have this idea of erosion. So that is interesting. And here is a simple case where we change the value of sigma of the diffusion. That is the original image, in this case an image. It's the simple example of a graph with the uniform sampling. So as soon as we increase the value of sigma, we're gonna shrink the object. That is the idea of erosion on the graph, and dilation is the opposite effect. We are spreading the information of the light point of the light node to the others. But one important one nice property that we found is basically with tau. We know that it's in 0 is dilation and 1 is erosion, but what happened with the tau is close to the middle. So we show that basically by taking account to these two papers, that in the case of tau equal to 1/2, is basically one iteration approximated motion by mean curvature. So that is quite strange. So there's some comment is because there are many papers doing similar stuff. So here, basically, we say that we are doing one iteration on mean curvature, that the definition of this curvature is different than the other authors. In this case, that these 3-4 authors, we are using definition of the curvature basically by means of isotropic total variation. And to understand what we are doing with this tau equal to 1/2, the best way to visualize the result is where by iteration. We know but these two papers that the iteration of this operator converge. And this is the 3 results, that is the original image, and what 2 results by changing the value of sigma. So basically what we see is that we are going we are converting to what we call a minimal surface. So basically, we integrate the curvature on the border of the image. We want to have a curvature close to zero. I mean, discrete of zero is a minimal surface. So we have only to show some result. That is the original value. That is by iteration, this operator with tau equal to 5 to 1/2. In different cases of sigma, we have this structure that we have that is simple, minimal, the closest minimal surface to the original one. So that is nice. That is one example where we have a graph. We only have signals where we have a value different to the white one. So we have a weird graph. We have some signal on the graph. If we do this kind of diffusion, that is like blurring the image. Erosion and dilation. Erosion, shrinking light object, and dilation is the dual operator. We have some, complete family of operators that we are, by changing the value of tau, of course, by changing the value of, okay, sorry. So then I'm going to show only one example. We have some application to machine learning. It's basically, we have a graph of image, and with the connectivity related with the similarity of these things. So we can apply this idea of something erosion or dilation, but it's not so funny because we lost information of where. But one interesting point is this mean curvature filter, because what we are doing is we start with this kind of digit. For example, that is the sample that we are considering. We build a graph from this digit. As soon as we increase the number of mean curvature iterations, we're going to see that the digits are regularizing between them according with that relationship. So basically, what we use this procedure as a way to regularize the sample that we take on the image or on the database by this idea of similarity on the graph. So we can see that at the end we were really close to have a classification, a binary classification. So that's all. Okay. Thank you for your attention.